Increasingly across the world of motorsport, we're seeing more and more adoption of pneumatics within race cars. There's a couple of really widespread uses that we see in race cars, one of which is the air jacks within GT racing. These are devices that lift the car off of the floor during a pit stop to enable the mechanics to change the tyres. Another system that we're seeing pneumatics used in is gear shift control. It's a very fast way of shifting a sequential gearbox. And unique to Team BRIT, we also use the pneumatic system to control the brakes. That allows us a couple of really big advantages. One of which is that we can control a huge amount of force that we're putting into the brake system. Previously, when you need to add that kind of level of hydraulic force into a system, what you used to be able to use is an electronic system. But the electrical load demand at that point to put that amount of force is very peaky. You have a huge amount of electrical demand in a very short space of time. A pneumatic system allows us to actuate those hydraulics by increasing the amount of force that we've got in the system in a linear way. It also allows us to gradually generate that pneumatic pressure and store it in a way that is safe and reliable and easy to deploy when we need it. When we first started developing the hand controls here, the design ethos was always that a disabled driver was never allowed to be at a disadvantage to an able-bodied competitor on the racetrack. With that in mind, we set ourselves a challenge. That challenge was for the driver to have complete control of the vehicle using only their hands through a high-speed to low-speed chicane. A really good example of that is the bus stop chicane at Spa, a really famous circuit. So you might be in sixth gear, coming in at 160 kilometers an hour into a real heavy braking phase. Going down the gearbox, you're exiting that chicane at maybe in second gear. Throughout the whole course of that complex of corners, you need complete control of the steering wheel, so you've got resolution of steering control. You also need to overlap the brake and the throttle and downshift through the gears through corners that are going opposite lock to lock. You couldn't do that with the original technology. The existing technology that was on the market was a push-pull lever, which is a mechanical lever that's attached to the brake and the throttle. You would completely lose control of the race car at that point if you were trying to go at the kind of pace that the drivers needed to get through there and you were using those control methods. And so really the genesis of our requirement for a pneumatic system on board to control the braking system was that we needed to isolate that control and we needed to have complete control of it at all times. So the signal path that we're using there to achieve brake control starts with an electrical signal on the paddle. We're using a position sensor that senses the position of the brake requirement that the driver's putting in on the steering wheel. From there, that electrical signal is converted to a pneumatic pressure using a proportional valve. So we're taking an electronic signal, let's say 70%. We're then converting that to a pneumatic pressure. Again, that's going to be 70% of whatever the maximum brake pressure is mapped to. That pneumatic pressure is then acting on a hydraulic system, which ultimately is the thing that's acting on the brake caliper to slow the vehicle. Here we've got the pneumatic components that are at the heart of the braking system. So the first stage for us within the pneumatic system is to generate the air pressure, which is done with this compressor here, the black unit. That's just an air pump, and we work at around 10 bar with this system. After it comes out of the compressor, it's important that we remove all of the moisture and any particulate matter. So we filter the air at the next stage, just here. From there, it goes into two air receivers, which are these silver tanks. These are accumulators for that air pressure. So these are run from a pressure switch, and that pressure switch then turns the air compressor on and off as demanded to keep that air pressure in between 8 and 10 bar. What happens next is the clever part, really. So that air source is then generated and then passed through the proportional valve, which is here. This is the part that we spoke about that takes the signal from the driver and converts it into an air pressure. That pressure is then output from here to the actuator. The actuator serves almost like a foot on a brake pedal. So we use a pneumatic ram, a pneumatic piston that pushes on hydraulic master cylinders. Those take the form of the brake pedal in the car, if you like. And so we're replicating the action of a driver's foot on a pedal using air pressure to push that pedal. When we first started developing this pneumatic braking system, we had a couple of concerns about the performance of it. First and foremost was probably ensuring that it was really direct link in terms of time. There's no delay in the system, and that was really key in designing it. Like I said earlier, we got through that by making sure that the fittings and the air supply system that we used in the system was of a sufficient flow rate to make sure that there wasn't any lag there. The other concern that we had was the lack of direct feedback for the driver during braking. We were concerned really that the driver wouldn't be able to sense the brake feel in the same way that they would if they were using a brake pedal. It turned out that that wasn't a consideration that we need to be concerned about. And actually using a hand control brake is a lot more straightforward in terms of the input that the driver feels during the rate of deceleration in braking. And so it meant that the driver is much more quickly able to adjust their brake input during braking to achieve a maximum deceleration performance. Really the beauty of the pneumatic system like this on a race car is that it allows us to store a huge level of energy that we can deploy really quickly and really accurately, as well as deploying it repeatably. At the heart of the system lies a Festo valve. Some of the engineers watching this might be familiar with that valve that's used quite widely in an industrial automation and production setting. So that's how the braking system works on the cars here at Team BRIT and how it enables our drivers to win races and to ultimately win championships. Thanks for watching, and don't forget to like and subscribe for more engineering insights.